Hello, this is chapter 11.3, and in this chapter we're going to discuss the following key concepts: the use of protecting groups to minimize unwanted side reactions involved with alcohols, the epoxidation reactions to form a cyclic ether known as an epoxide, and the subsequent acid-base catalyzed ring opening reactions of those epoxides. Here is the video breakdown. There will be two videos for this particular lecture. The first one covers the use of ether and silyl ether protecting groups for alcohols, and then in the second video we'll discuss epoxidation reactions and the subsequent ring opening via acid-base catalysis. I want you to imagine the following scenario. You're going to paint a wall, however on that wall there are a number of gold electrical fittings that you really don't want to be covered in paint. Now you have two choices here. A, you're super careful and you paint around each electrical fitting really carefully. But of course you know that this is going to take a very long time to do, and that's because there are quite a few fittings. Now choice B would be to protect those fittings with tape and some sort of covering such that you can paint the wall but not the electrical fittings. Later on, and at a point of your choosing, you can easily remove the tape, remove the cover, and then admire your newly painted wall and your gold fittings. This analogy can be extended to organic chemistry. At certain times, you're going to want to mask the reactivity of a functional group so that it does not react, and this is where a protecting group synthetic methodology comes into play. Protecting groups are a chemical modification of a functional group used to make it temporarily unreactive. And just like when you take the tape off the newly painted wall, the removal of the protecting group is called deprotection. Here we have a molecule with two functional groups, an alcohol and a minor functional group, the halogen group. The intention of the reaction is to have a carbon-carbon bond-forming reaction via SN2. However, if you were to try this reaction, you wouldn't isolate any of the desired SN2 product. So what went wrong? Well, let's not forget that the acetylenic anion can also behave as a base, and so an undesired acid-base reaction will happen far quicker than the SN2 reaction. So, what's the solution here? Many reactions are not chemoselective. Chemoselectivity is the preferential outcome of a chemical reaction over a set of possible alternative reactions. We wanted SN2, but we got the alternative acid-base reaction. The solution, of course, is to add some sort of protecting group, which we've labelled PG, to our alcohol, and this would stop the acid-base reaction from occurring and allow the SN2 reaction that we originally desired. Let's look at a potential protecting group strategy now. One of the methods that we can use to protect this primary alcohol substrate is through the formation of a tertiary butyl ether. We'll look at the mechanism for this protection step on the next slide. The next part of the reaction, once the tert-butyl ether group is attached, is to perform the desired SN2 reaction to give the desired alkyne product. The last step would involve the deprotection, and this would give back the original alcohol. Organic chemists often depict multi-step reactions using a series of offset arrows from the reagent to the product, but please note that the number of these arrows is not indicative of the number of steps for that multi-step synthesis. Tert-butyl ethers are common protecting groups for alcohol substrates. The reaction 1 and 2 seen on the last slide are carried out first before the addition of the alcohol substrate. So 2-methylpropionene is reacted in an addition reaction with sulfuric acid, and the tertiary carbocation is formed as seen as part of this reaction sequence. Now the alcohol is added and behaves as a nucleophile reacting with the tert-butyl carbocation. This yields a protonated ether, and the acid catalyst is regenerated by deprotonating the protonated ether to give the tert-butyl ether protecting group and the original sulfuric acid catalyst. As we know, this molecule undergoes an SN2 reaction, but what about that last step, which was the removal of the tert-butyl protecting group via deprotection? Let's have a look at the deprotection mechanism for this reaction on the next slide. This time, the reaction is carried out in catalytic sulfuric acid under reflux or heat conditions. The tert-butyl ether is protonated, and this makes the protonated alcohol to the right-hand side a good leaving group. Because the tert-butyl carbocation is stabilized through hyperconjugation, this is immediately attacked by water that accompanies the aqueous acid. In a subsequent proton transfer, tert-butyl alcohol is formed. This gives a deprotected alcohol as seen here, and also gives us tert-butyl alcohol. The method that we have just seen involves the use of acid and heat, and these are both quite harsh conditions in the organic chemistry world. Therefore, it's possible to achieve a deprotection method using much milder conditions, but for this, a different type of protecting group strategy is employed. Let's now meet the Silyl ether protecting groups. Now, these are advantageous for a number of reasons. Firstly, the protecting group forms a strong oxygen-silicon bond, which means it's stable to use with nucleophiles and carbon or nitrogen bases. Secondly, the Silyl ether protecting groups usually require much milder conditions for their subsequent deprotection. So how do we make a Silyl ether protecting group using an alcohol? A common Silyl ether protecting group is formed by the reaction of an alcohol with tert-butyl dimethyl silyl chloride in the presence of imidazole, which behaves as a base. There are other choices of silyl chlorides available, like trimethyl silyl chloride, but these are relatively unstable and are not a first choice of reagent. The OH group reacts with silicon, and this forms a very strong bond, as previously mentioned, and the chloride is kicked out. When the chloride is kicked out, this deprotonates the hydrogen, forming a molecule of HCl. The additional HCl that is generated in situ by this reaction is neutralized by the imidazole base, and this avoids it reacting with the alcohol. Let's now talk about the deprotection strategy that's used for Silyl ether protecting groups and look at those milder reaction conditions. The main advantage of the Silyl ether protecting group is how easily they're cleaved. No acid and no heat in sight here. The silicon-fluorine bond is very strong, even stronger than that for silicon-oxygen. Therefore, in the deprotection step, the addition of a source of fluoride ion, that's F-, will lead to the cleavage of the silicon-oxygen bond without affecting the rest of the molecule. A typical source of fluoride ions is the salt tetrabutyl ammonium fluoride, aka TBAF.
This concludes part A.
In this video, we're going to discuss a specific type of cyclic ether known as an epoxide. These are cyclic ethers that are three-membered rings, e.g. an oxycyclopropane. On this first slide, we see that the synthesis of these three-membered cyclic ethers is caused by the reaction of an alkene with a reagent known as m-CPBA. This stands for metachloroperoxybenzoic acid. So these are peracids, and peracids have an additional oxygen atom in the carboxylic acid group, as shown. The mechanism for this reaction is beyond the remit of this course, but knowing the stereochemical outcomes is not. So just like in previous lectures, we see that the cis-butene will lead to a meso compound via a syn stereospecific addition across the double bond. The attack of the alkene substrate comes equally from above or below the alkene. However, because of the symmetrical nature of this alkene, this sets up an internal mirror plane within the product, and this type of alkene substrate results in a meso compound. And just like before, when using a transalkene such as trans-butene, the syn addition results in a racemic mixture. In this case, we're showing the enantiomer where the syn addition came from the top side of the double bond. Please note that epoxides are very strained, and so this makes them like coiled springs. They are a very reactive and very useful synthetic tool that is used by organic chemists. Let's see how these can be ring opened in the next part of this lecture. As aforementioned, the ring strain makes an epoxide very reactive on the addition of a nucleophile. In addition to this, symmetrical and unsymmetrical epoxides result in good regio and stereo control on the addition of a nucleophile. Time for some more SN2 and SM1 styled chemistry. There are two types of epoxide ring opening reactions. These are either acid catalyzed or they are base catalyzed. A general mechanism is now shown for the reaction of acid catalyzed ring opening on this slide. The oxygen lone pair of the epoxide reacts with the catalytic acid, in this case a hydronium ion, and becomes a protonated epoxide. It is now possible to think of this protonated epoxide as a leaving group. The protonated epoxide reacts with a nucleophile, and like SN2 for a symmetrical epoxide, the epoxide carbon-oxygen bond is cleaved and the ring strain released as the nucleophile approaches from the back side. We now have a protonated trans 1,2 diol. The last step is simply a proton transfer to yield the trans 1,2 dihydroxylated diol and also regenerate the acid catalyst. But what if we have an unsymmetrical epoxide? When there is an unsymmetrical epoxide like the one that we see on this slide, then the ring opening behavior of the nucleophile is like SM1. So the protonated epoxide here has the carbon that is more substituted, and this resembles a tertiary carbocation. The weak nucleophile, that's methanol, comes in and attacks at this particular center, which is just like the SN1 reaction. Here we also see the overall reaction scheme and the subsequent deprotonation of that methanol to produce the ether. Let's now have a look at the base catalyzed ring opening reaction. With a symmetrical epoxide, the general theme is the backside attack that is characteristic of SN2 on one of the carbon-oxygen bonds of our epoxide. This opens the epoxide and yields an alkoxide intermediate that has anti-stereochemistry. Via proton transfer, the alcohol of the strong nucleophile is deprotonated to regenerate the strong nucleophile. This step is the regeneration of the base catalyst and the subsequent formation of the trans 1,2 diol. So again, what happens if there is an unsymmetrical epoxide? The less hindered side of the epoxide is attacked by the strong nucleophile in this case. So this is the reaction of epoxide with methyl oxirane. The primary carbon is attacked because it's less hindered, and this should sound reminiscent of SN2 reactions. The exact same reaction scheme occurs here as shown in the mechanism above. The alkoxide is formed, a proton transfer occurs, and this regenerates the epoxide anion. This reaction also proceeds with anti-stereochemistry.
This concludes Part B.